Our next speaker is Daphne Klotsa from the University of North Carolina, Chapel Hill. She will actually tell us about a model of a spring big model, I guess, of a single swimmer, right? Mechanism or sort of a minimal swimmer model. Thank you.
Hello, can you hear me? Is it working?
That's one.
Hello? Okay. I'll shout.
Can you hear? Yes?
I'll try. I'll speak loud. So my name is Daphne Klotsa. I'm an assistant professor in Chapel Hill in North Carolina. And today I would like to tell you about a system of active matter that I find very interesting. So hopefully you will too. First, I would like to thank my collaborators at the University of Nottingham, Michael Swift, Roger Goldie, and Richard Hill, as well as Kyle Baldwin. So first, a brief definition of active matter, since this is an active matter conference. I think there are many, but we can describe active matter, we can say, describes out of equilibrium systems that locally convert energy into motion. And this is a slide that shows some of the examples that sometimes we have in mind when we think about active matter, some of which were covered already, like this one in the anthrax. So here we have robots, fish, ants, and so on. They cover many length scales. But I would like to particularly focus on systems where the active particles actually use the surrounding fluid in order to move. Okay, so these are just three examples. This is krill, these are fish, and these are birds. And if we do that, if we focus on these systems, we can make this plot where basically we have the velocity of the particle, of the organism, as a function of the Reynolds number. Now the Reynolds number, since we're interested in the fluid of these systems, then we need to be able to describe the fluid. And the Reynolds number is a good measure of giving us some information about the fluid. So the Reynolds number is a dimensionless ratio of the inertial forces over the viscous forces. And in our systems, we can define it as the characteristic speed of the organism times the characteristic length, the size of the organism, divided by the viscosity of the surrounding fluid. And so if we do that, we get this plot. So this is the Reynolds number. And we notice two things. One is that in nature, the organisms that the Reynolds number spans more than 10 orders of magnitude. Okay? And we can also identify three regimes. So there is a regime here where it says pure viscosity effects. So here, the organisms are very small. So these are microorganisms, bacterial cells, or nanoparticles. And here's where viscosity dominates. Okay, so this term is very large. At the higher Reynolds number, and what we have is birds, whales, ships, and airplanes. And here, inertia dominates. And there is this regime in between as well, where we actually have a lot of organisms. Of course, this doesn't stop. Small animals and so on, where we have influence of both components. So both inertia and viscosity play a role. They're comparable to one another. And this is what we'll call the intermediate Reynolds number regime. If we go back to the low Reynolds number, so this is the limit that in the active matter community has been studied mostly. And here, at low Reynolds number, we have what is called so we assume that there is no inertia, and we have what is called the scallop theorem, which basically tells us, so this is a scallop, this is going to be the scallop for a moment. And what we have is that we know that the reciprocal strokes do not swim. This is because there is no inertia. And so if we were to look at the cycle of a scallop moving, it will close its shell, it will move back. Okay? But then the second half of the cycle, it will go back to exactly where it was. And that's because we have Stokes equations that are linear. There is no time. So we need to break time reversibility. And this is what organisms do by chirality, for example. This is the flagella. And in this low Reynolds number regime, there is a lot of work and a lot of very interesting emergent behavior that we see. This is just one example of what's called bacterial turbulence, but there are many other papers and phenomena that are very interesting. But if you look at this plot more carefully, what you'll notice is that actually there's no clear transition between the low Reynolds number regime and the intermediate Reynolds number. So we know that when we're over here, probably inertia does play a role. We're intermediate, we need to consider both components, viscosity and inertia. When we're very low Reynolds number, we think we're okay making the assumption that there's no inertia. But in fact, you see there's a dashed line here, and it's not clear where this transition takes place. So how do these low Reynolds number systems change as you increase inertia? And in particular, I think this is a very important question when you consider that you have these organisms that perhaps are not the tiniest ones, but are somewhere here. And what we're interested in active matter is a large number of them. So when you have large groups of small swimmers, perhaps the relevant length scale is no longer that of the swimmer, but that of the group. And if that is the case, then that would go into the Reynolds number here, and you might have an effective Reynolds number, which is higher than what you think you have. In which case, maybe you need to consider that, and just assuming that you have no inertia is no longer valid. So we wanted to design a swimmer that will let us study this transition. And so the simplest swimmer we could think of is a reciprocal swimmer. That means that it's something that does not swim at low Reynolds numbers, but should start swimming at some point, and we want to see how that will happen as you increase the Reynolds number continuously. So this is our simple reciprocal swimmer. So these are two spheres connected by a spring. So two spheres and a spring make a good swimmer. This was the title of my talk. This is why. And this is a cycle of the oscillation. And the experimental realization of this is this one here. So we have a plastic and glass spheres. The big sphere, the gap between the two is 3 millimeters. This is a neutrally buoyant object. And we put it in a cell, and then we shake the cell, and this thing takes off sometimes, and sometimes it doesn't. It stays stationary. And so we do this for a range of frequencies, amplitudes. So the gamma is the dimensionless acceleration. So A is amplitude, omega is the frequency, and G is the gravitational acceleration. So we do it for a range of amplitudes, two viscosities for the experiment, and a typical speed would be maybe about 1 millimeter per second. So if we do this, what we actually find is the following. So this is the velocity scaled by the frequency and the characteristic length as a function of the Reynolds number. Now you will see here you can use different, you can define different Reynolds numbers depending on your system. And the one that was more relevant for us was what is called the streaming Reynolds number. And here the length scale is, the characteristic length is the amplitude of the oscillation. So this is what A squared is. Omega is the frequency and mu is the viscosity. So if we do that, what we find is that our data collapses on this curve. So this is all experimental data, and the crosses are simulation data. Okay? And this is an inset, the one typical trajectory. So what we actually see is that it looks like there's a critical onset in the Reynolds number, beyond which you get swimming, but below which there's no motion. So the object is vibrating in place. Okay? So it looks like this is a discontinuous transition. And you can see these are simulations. So I can talk about the simulation model in questions if you're interested, or afterwards. But this is done for 3 viscosities. You can see it's the same curve, but the data is a little bit cleaner. But again, we see that it looks like there's a critical onset around between 30 and 50 Reynolds number. But so I'll show you quickly this movie. So this is what happens below the critical Reynolds number. So hopefully you can see this vibrating in place. And this is what happens when you're above the critical Reynolds number. So this actually swims. But the reason, but we would like to understand a little bit better what is going on. And so what we did was, with the simulations, we can look at the fluid flows. And what we find is this. So when you have, so this is a single swimmer, and in the simulation, there's no actual physically spring. So this is what the average fluid flows look like. So the crosses are the centers of vortices. And what you see is that for the stationary swimmer, each sphere has 4 vortices around it. Okay? And in fact, if you go to the literature, which I don't have time to show now, what you will find is that, in fact, this is the fluid flow that you would find if you had an isolated sphere vibrating at these Reynolds numbers. This is what the average fluid flow would look like for each one. But when the object is swimming, what we find is that two of these vortices have been swallowed up, and what we actually see is this collective fluid flow that is around the swimming object. And so we don't know what causes what, and we're trying to figure out, but this was further evidence that this is a discontinuous transition between the stationary object and the swimming. And so with that, I would just like to leave the open question of what is the collective behavior of this thing. So this is really what our goal was. This is why I'm here, because I'm interested in the active matter of these organisms, of real organisms, but also model systems, as inertia increases. What is the collective behavior? Can we move that onset by having a lot of swimmers swimming together? What is the role of boundaries, and how do real organisms utilize inertia, the ones that are close to this transition? And with this, I would like to take your questions. Thank you.
Okay, we have a question. Are you still there? Come on.
Okay. Yeah?
Yeah.
Dr. So I'm unclear. Is your swimmer's force-free? Like the principal moment of this is dipole?
Yeah.
Yeah. Okay.
And in this relation, you say there is no spring, but on average it is a fixed distance?
There is a spring, it's just that physically, like if you look at the flow, so in reality, if you were to look at the flow, it would be, because there's a physical spring there, it might change slightly the flow.
Or
because there is
what you mean
something
that there is no,
between,
there is
yeah,
just
yeah.
a constraint.
But, yeah.
That's what it is.
But I don't think that's dominant.
Okay, Jeremy.
Can you say one more word? How is it force-free experimentally? I don't really understand how it could be. How would your experiment compare with this flow, which is force-free? Your experiment, you have to force it.
So the experiment, you shake the container. And then this thing at some point resonates and it goes off, or it
So you
doesn't.
think it's force-free? Have you looked at the PIV around your swimmer?
No, we haven't. But we can't, but it would be very interesting, yes.
Yeah, I don't know what would be.
Yeah.
Actually, function for young from solid or mass. Actually, we have experimented data can make it bigger, but it's in microscale. So using the vortex around the host sphere, because the center is the part of diameter around 1 micron.
1 micron?
Yes.
So I think, so there is something that, so at low Reynolds number, if you're at very low Reynolds number, then you won't get this flow. So this is the kind of flow that you will get as you increase the Reynolds number and you're towards this intermediate regime. And the reason is because at low Reynolds number, you have this, if you move a sphere, just a sphere, right? Forget the two things, the two spheres in the spring. If you just have a sphere and you move it back and forth at low Reynolds number, on average, the average flow you will get over a cycle is 0. Because the second half cancels the first half, right? If you're at low Reynolds number. So I think a 1 micron is quite small. But I think it's interesting to test it, especially for larger groups. But when you're at these intermediate Reynolds numbers, what you have is you would move, so the first half of the cycle, the second half of the cycle does not cancel the first half. What you actually get is an average fluid flow, which is quite complicated, and in fact it looks like this. But I can tell you more about that, yeah.
Okay.
But just to clarify, I mean, every streaming flow, there are two Reynolds numbers. There's the primary Reynolds number of the actual oscillatory motion, which has to be substantial, and at least greater than 1. And then there's a streaming Reynolds number, which can be small, and nevertheless you get streaming, or which can be substantial, and you get a different kind of streaming. So I guess to maybe clarify the question, is it necessary that the streaming Reynolds number is substantial in order for this kind of effect to happen?
So there are the problem with it, one of the problems with this system, and correct me if I'm misinterpreting your question, but one of the problems is that you can define many Reynolds numbers actually. So you can even for the oscillatory motion, right? So assume that you have omega and mu here. The length scales that you can take are many. So you could have the amplitude, you could have amplitude times the size of the object. You could use a boundary layer length. There are the oscillatory boundary layers. So what we found was that this definition, we can call it, it's called streaming Reynolds number, but that with this we get this collapse. So we think that's the most relevant. But the other Reynolds numbers, and I can go into more detail after, are never really far away from this number. But that's partly because in this experiment, and in these intermediate Reynolds numbers in general, all the length scales are quite close to one another. So this is a bit of a problem as well to identify which Reynolds number is the correct one, theoretically speaking, analytically speaking, because they're also similar. All the lengths are very similar.
That's probably easier in a microscale system, actually.
Okay, let's just take one last question and then.
Isaac Cross from the University of Michigan. My question is, if the spheres are the same size, you'll get no net motion. And the other regime, if one is many times bigger than the other sphere, you'll get no net motion. So do you have an idea of what size difference will give you the most amount of motion?
Oh, that's a good question. No, so this is new work. I think there are a lot of questions to explore actually, but that's a good point. I have done, in simulations it's actually easier because the experiment is very hard to get everything neutrally buoyant and do things over many, systematically. But in simulation it's something I should be able to do to see exactly how. So I have done it a little bit, but I have only 3 measures, they're the same, one is twice the other or half the other, and that's it. But it is a good point, to see how systematically that changes the behavior.
Okay, let's thank Daphne.